Hello, Analysis 1B, and welcome. Today we are going to look at arc length. In doing this, we will review the mean value theorem so that we can derive the arc length formulas. We're going to be looking at, I would say 4 actually. I have 3 written here, rectangular, parametric, and polar, but we'll be looking at functions of x and functions of y in that rectangular subsection. After we look at the formulas, we'll get them all down on one slide, and then we will hit some examples. If you are following along in the book, which Mr. Schwartz and I highly recommend, this lesson jumps around the textbook. We're looking at sections 7.4, 10.3, and 10.5. Because we're looking at all of rectangular, parametric, and polar in one lesson, that appears several times in the book. Let's go ahead and get started. Alright, to get started, I want you to ask yourself the question, what is the mean value theorem? Alright, and don't just ask yourself the question, also try to answer that question. What is the mean value theorem? Also, what is necessarily true if one is to utilize the mean value theorem? Right, what is true about a graph if we are going to implement the mean value theorem? So for me, to answer this question, I'm going to give myself a graph, right? That's an arrow. That kind of, here's a graph. Whee! And I'm going to look at the slope from the initial point here, which I'm going to call x1, y1, and then the final point here, x2, y2. All right, this slope, which I'm going to call m, is y2 minus y1 over x2 minus x1. All right, that's the slope between these 2 points. Right? What does the mean value theorem say here? All right, before I say anything, I'm going to go ahead and give this curve a name, this function a name, f of x. So the mean value theorem states, as long as certain criteria are met about this curve, it states that there exists some value between x1 and x2 such that the derivative of the function is equal to the slope. Right? It says that there is a value between x1 and x2 such that a value exists. Now, it doesn't tell us where it is, but it tells us it exists. Now, this value is between x1 and x2. Right? Take a second to try and find out where that point is. Right? It doesn't say that it's in a specific spot. It says that it exists somewhere. Right? And I have this slope here, this secant line between x1, y1, and x2, y2. And I just need to find out another point that has that same slope as its tangent. And I would say that's about right here, right? Right. So in this interval x1 to x2, this is where my point C is, right here. All right, but before we proceed, I want to be clear. Right? The mean value theorem only works when something is true, and I want you to think about what that something is. Right, when is the mean value theorem true? The mean value theorem is true. Let me go ahead and change the color here. The mean value theorem is true when f of x is smooth. The mean value theorem works when the derivative is continuous, when the derivative function is continuous. And why does that matter? Right? Let me just draw in this little space I have right here an example where the mean value theorem is ineffective. Right, here is a function. Right, it is not, well, it is continuous, but its derivative is not continuous. Right, if you were to take the derivative of this function, you would have a discontinuity. Right, here is my initial point. Here is my final point. Right, the secant line between these two. All right, it has a slope of 0. And if you look, there is no point at which on this graph the slope is 0. There is no point between x1 and x2. There is no c value that is going to give you a slope of 0. And that's because there's some crazy bonkers stuff happening right here. Right? Our slope is not continuous at this point. Right? This is not a smooth curve. So the mean value theorem is not going to work here. Now we do have a workaround for when it comes to arc length, which we're about to jump into, but we cannot use the arc length formulas that we are about to derive on this curve in its entirety. Let's continue. Now that we have the mean value theorem out of the way, all right, we want to remember the mean value theorem as we proceed here. All right, so how do we calculate arc length? Let's go ahead and give ourselves a graph, as we always do in pretty much every scenario in math. Let's give ourselves this graph right here. And what I want to do is I want to describe this graph. And there are many ways to describe this graph. You can describe this graph as a function of x, right? F of x. Right? But you can also describe this graph as a function of y. We have in many times looked at functions put in a y, output an x. So that's absolutely valid, right? Plug in x1, here's x2. Right? You can plug in y1, plug in y2. Right? We move in the positive 0 to infinity direction. Right? What other ways can we describe this curve? Right? We can describe this curve using parametrics. So let me go ahead and give these bullets. Right? We could say x of t, y of t. Right? And t1 might be down here, t2 might be up here. Let me go ahead and put this x1 down here and this x2 over here. Just because now, right, when we think about parametric, which I've just drawn here, right, this might be our t1 and this might be our t2. And we can also describe this curve using polar. So r is equal to a function of theta. Right? We can describe this curve in several different ways. Right? And what we need to do is break it down for each and establish how do we calculate the length of this curve. That is our goal here. How can we find the length of this curve? Let me go ahead and add theta 1 here and theta 2 here, since as Mr. Schwartz talked about in his previous video, when he reviewed polar, this is the direction by which we graph in polar. We start with an angle with the positive x-axis, the polar axis, and we move towards the positive y-axis. So how are we going to find this length? How do we find length, or how do we find quantities in calculus? Think about that. Right, what we're going to do is we're going to look at a sliver. Find the length of this sliver right here. Let me go ahead and change the color so it's a little bit more obvious. We're going to find this length, and then we're going to do that an infinite amount of times along the curve, from t1 to t2, from theta 1 to theta 2, from x1 to x2, from y1 to y2. We're going to find an infinite amount of infinitely small lengths, and this is going to end up being a Riemann sum. So what is the length of this green curve? Right? Let's go ahead and call it delta L for length. Right? What is the length of this small curve? Or at least, how can we approximate this length? Okay, in order to approximate this length, let's just go ahead and pretend that it's a line segment. How do we find the length of this line segment? All right, it has a change in y, and it has a change in x. All right, so what is the length of this line segment? It is the square root of dx quantity squared plus dy quantity squared. That is the distance formula. It's also just the Pythagorean theorem. And what's nice is change in x, change in y, this formula right here, it's true no matter which function you pick. No matter which way you describe this curve, this is still going to be true. What we need to do now is we need to turn this into a Riemann sum and then into an integral. Right? And then we can just simply calculate. Right? The hardest part about arc length here is knowing what the integral is. Once you've written the integral down, all you got to do is do what you've done many times and evaluate. Okay, so we need to turn this into a Riemann sum. All right, the problem is we don't have we have a delta x, right? If I want to write this this integral as with small partition dx, we have a dx, but it's within this square root, so we need to do something about that, right? And if we're doing this with respect to y, we're going to need a dy outside of this radical. Right, so we need to do something about that. So we need to introduce it somehow. All right, let's take this to the next page. Okay, so here we are. I need to figure out how I can introduce a delta x into this that's not under the radical. I guess one thing I could do is factor out a delta x. I'll get a dx underneath here. Let's see if this works. I'm going to get 1 plus delta y squared over delta x squared. And then, oh, look at that. Right? I can take this delta x out. And I get a 1 plus delta y over delta x, all right, squared. I have a delta x down here now, but I have a delta x on the outside, so I can take a Riemann sum, all right, with respect to x. All right, but what can I do with this dy over dx? All right, dy over dx, that screams like derivative. Is that valid? Dy over dx, derivative. Can I just replace dy over dx with like the derivative of the function? Right? Can I just do this? Right? Because if that's the case, not a dx, but a delta x, if that's the case, then I'm home free. I can just take a Riemann sum and turn this into an integral. All right? And then I have this derivative within my integral. Is this move valid? Is this move valid? Let me go back a page. Boom. All right. dy over dx, sorry, delta y over delta x. Put that right here. Right. Is there a point between this point, let's call it xk, and this point right here, let's call it xk plus 1. I'm going to write that down here too. xk plus 1. Is there a point between x sub k and x sub k plus 1 such that the derivative is equal to this slope? Right? Is there a point somewhere between these two where the derivative of the function is equal to delta y over delta x? Right? Let's go, it's going to be yk plus 1 minus yk all over xk plus 1 minus xk. Is there a point between here, let's call it like C, where the derivative evaluated at C is equal to the average slope? Is this curve smooth? Yes. And the answer is absolutely. And that's why we reviewed the mean value theorem. Right? As long as the curve is smooth and the derivative is continuous, there exists a point between your endpoints such that the slope is equal to the derivative evaluated, the secant line, the average slope is equal to the derivative evaluated at that point. Right, so let's go back to where I was, right here. This move right here is absolutely valid. Right? I can replace delta y over delta x with the derivative of x, because there exists a point between xk and xk plus 1 where the derivative is equal. Now you may say, wait, but we are taking finite lengths. We are going to take the Riemann sum as the lengths get smaller and smaller and smaller. So I don't care where that point is between x sub k and x sub k plus 1. Right? Because as I get smaller and smaller and smaller, that point C becomes x sub k. All right, let's go back a page one last time. We have found this length. Let's go ahead and find all the lengths and add them up. Let's take a sum. So we have the sum of the square root of 1 plus the derivative, right, quantity squared, delta x, and we're going to be making delta x infinitely small. We're going to take the limit as the magnitude of delta x goes to 0. Right? When that happens, we turn it into an integral. We're going from our starting point to our ending point, which in my example previously was x2, and we have 1 plus the derivative quantity squared dx. Right? And this is the arc length given a small change of x. Right, what is that going to be for a small change in y? What is it going to be for a parametric? What is it going to be for polar? That's what we're going to look at next. But this is arc length given a function with respect to x. This is the length of the curve. All right, the big thing here to just quickly readdress before we proceed is we were able to turn that dy over dx into a derivative because of the mean value theorem, right? And because this curve is smooth, right? Arc length gets a little bit more complicated when the curve is not smooth. Right? So be very careful. This is only applicable when we're dealing with a function that has a derivative that's continuous. We are going to be looking at tons of theorems throughout this semester that have prerequisites that are necessary to recognize before you begin a problem, because that problem that I give you might not allow you to use the arc length formula. Right? If our derivative is not continuous, then we're going to have to do something. We're going to have to partition our curve into continuous segments. All right, now it's time to continue. Let's look at if our curve was a function of y. Right. What about f of y? All right, a function of y. Well, spoiler alert, it is the exact same thing, right? Because the distance formula is the exact same thing. All right, no matter which way we do this problem, the distance formula is still the Pythagorean theorem. So let's say I have a curve, right? And I have, let's say I have a y1. Let's say I have y2. Right? Let me put them on the graph. y2, y1. Right? Let's say I have some small sub-interval, and let me get another color going. Let's not use green this time. Let's use purple. Right? Let's say I have this. Oh, that is not purple. That is purple. Let's say I have this little segment right here. Right? Let's call it a y sub k plus 1. Go ahead, add those to my axis. Right, what is the length of this curve? Let's look at the length of this curve, and then let's do it an infinite amount of times. All right, and the length of this curve is still delta x by delta y. Right, the quantity delta x squared, the quantity delta y squared, all rooted. All right, the delta L, right, the small length is still the square root of x quantity squared plus delta y quantity squared. All right, but now we want to take a derivative, or sorry, we want to take an integral with respect to y. So what do we need when we take the Riemann sum of this thing? We need a delta y. Right, so think about how you might do that. Right? You could do what I did earlier and factor out a delta y. This time I'm going to do it a little bit different. I'm going to introduce a delta y on the outside. Right? This is just another algebraic approach to establishing this integral, this Riemann sum. Okay? So this delta y I'm going to leave on the outside. I wanted to introduce it. This delta y is just a byproduct of introducing the numerator. So let's bring that into the radical. Right? We have a delta x squared plus a delta y squared. We're bringing this into the radical, which means it's going to be in the denominator and it's going to be squared. Right? So I think we get the same thing, right? We have a delta x squared. Oh, delta x squared over delta y, huh? Quantity squared plus delta y squared over delta y squared, that's plus 1. We have this delta y on the outside. All right, that was our goal. Here's smiley face. Delta x over delta y. Right? This is still a derivative, right? Delta x over delta y, that's just going to be the derivative with respect to y. Right? And can we turn this into a derivative? Yes. Right? And the reason why, once again, same as before, right, the air conditioning came on. The difference between this and before, the mean value theorem is still going to work. There's still a value between yk and y sub k such that the derivative of this function evaluated at that value, let's call it w, is going to be equivalent to the secant line, all right, delta x over delta y. All right, so we can, because of the mean value theorem, turn this quotient into a derivative, which is very convenient for us. Let me not forget my delta y, right? Because if I then look at the sum of this, right, delta y, right, as delta y gets small, this becomes the integral from y1 to y2 radical derivative plus 1. Let me not ooh, I'm forgetting something. What am I forgetting? The square. Right? I feel like that square is very often the reason why people get these questions incorrect. Why they make mistakes. They forget that square. And often when you forget the square, it actually makes the problem more difficult. So don't forget that square. dy. All right. Here is arc length if you are looking at a function with respect to y. It's the exact same thing, right? And you could even switch the 1 and the f prime just so that it looks like, let me see if I can go back, the function with respect to x. All right, so arc length, it's in general going to look very similar to the other forms. All right, continuing on. What about, you know what, I don't want to use purple anymore. Let's go back to something that's easy to see. All right, what about parametric? All right, and I'm not going to actually draw the curve again because I'm trying to justify the point. Right? No matter how we draw the curve, the distance formula is still going to apply, and we're still going to have delta x quantity squared plus delta y quantity squared. Right? How do we turn this into a Riemann sum with respect to parametric now, and then take that Riemann sum and turn it into an integral? What do we need to introduce for parametric? All right, for functions with respect to x, we introduced a dx. With functions with respect to y, we introduced a delta y. What do we need for parametric? And the answer is we need a delta t. And I'm just going to throw a delta t right in there. And then similarly to how I did delta y, I'm going to turn this into a Riemann sum. All right, let's just do the algebra. All right, I want this numerator delta t on the outside. Let's bring that delta t inside. I'm going to have my delta x quantity squared plus my delta y quantity squared all over, there's a dt out here, all over delta t squared, right? Because if I take the square root, boom, it's on the outside, right? Change in t, positive value, so we're going to have positive value on the outside. No need for absolute value. Okay, let's go ahead and rewrite this, right? Delta x over delta t squared plus delta y over delta t, quantity squared. We got that delta t on the outside. I don't know why I wrote a d there. I think habit. Sorry. All right, can I turn delta x over delta t, as I've been doing? Can I turn delta x over delta t into the derivative of the x function in the parametric curve? Right? And can I turn delta y over delta t into the derivative of the y function for the parametric set of equations. Right? Am I allowed to do this? Right? This is a much more complicated question than before, right? Because the mean value theorem says that on a curve, right, as long as that curve is smooth, there is a point on that curve whose tangent is equivalent to the secant line. Right? But what it doesn't say is that if I use the mean value theorem twice, one with respect to x and once with respect to y, is that point going to be the same point? Right? And as I get closer and closer and closer to, as I make my my delta L smaller and smaller and smaller, as I make this length smaller and smaller and smaller, one might be able to intuitively agree that this is a valid move here, right? From line, let's call this 1, 2, 3, from line 3 to line 4, right? You might intuitively be able to feel that I can, in fact, turn this into a derivative and this into a derivative, and you would be correct. But the analysis, the in-depth explanation is actually something that we will save for multivariable calculus. So we're not going to worry about that right now. Right? What you need to know is that we can use the mean value theorem with respect to x and with respect to y, and it is valid. Right? So we can continue. This move is valid. So let's go ahead and write this out again. We got a delta t on the outside. Let's go ahead and find the actual length. We'll throw a limit right here as delta t goes to 0. Right? And if we do that, we get, right, let's go ahead and just say t1, t2, right, the derivative of the x function with respect to t, quantity squared, plus the derivative of the y function with respect to t, quantity squared. Right? There is your arc length for a parametric set of equations. Right? If you want to find the length that a set of parametric equations makes in the plane, right, this is your function. All right, we got one more. Polar. And in my opinion, polar is the most interesting and the most difficult of the arc length functions. Right, we want to find the arc length of a polar curve. Once again, right, if you look at a little bit of a curve, it's still going to be approximated using the distance formula. Delta x quantity squared plus delta y quantity squared. But what we need to do is now we need to introduce the variable that is the variable in polar, which in our case is theta normally. Let's go ahead and introduce delta theta, right? Just multiplying by 1 here. Let's go ahead and bring in that delta theta, the denominator one. We're going to get delta x quantity squared plus delta y quantity squared all over delta theta quantity squared. Delta theta on the outside. Right, the whole reason for bringing this delta theta squared in is to have this delta theta on the outside to take a Riemann sum. And then let's go ahead and split this up into 2 fractions. You kind of see where we're going. It's very similar. Quantity squared. Delta y over delta theta quantity squared. Delta theta on the outside. Okay. How do we turn this into a Riemann sum? How can we use the mean value theorem? How can we turn this into some derivatives underneath this radical? Right, because when we're given polar, we're given a function r is equal to a function of theta. Like, I see no r's here. Right? What am I to do? What am I to do? Well, isn't polar just parametric? Right? What is x in polar? Right? X is r cosine theta. Right? Y is r sine theta. Right? So really, I probably should have given myself a little room. Let me go ahead and move this down. All right? X is f of theta times cosine theta, right? Y is equal to f of theta sine theta, right? Delta x over delta theta, that's just the derivative of x with respect to theta. Delta y over delta theta, that's just the derivative of y with respect to theta. That is what we're going to do, right? What I'm going to do is let's look at the derivative of x here, right? We get f theta times the derivative of cosine, which is negative sine theta, and then chain rule. Or sorry, not chain rule, product rule. Then we get cosine theta times the derivative of f of theta, which is just f prime theta. Right? Similarly, down here, y. Right? That's going to be something very similar. We're going to get f of theta times cosine theta, and then we're going to get minus cosine theta f prime theta. Oh, I think I made a mistake. This is going to be plus sine theta. My bad. Okay. We have the derivative of x. We have the derivative of y. Let's go ahead and plug these things in. And you know what? To do that, I'm just going to grab all of this stuff and take it to the next page. All right. Right. Because this is a little bit of algebra. Right. We're taking this stuff and we're plugging it into here. So the thing I'm going to do first is I'm actually going to say that delta x over delta theta, that is the derivative of x squared. Delta y over delta theta, that's the derivative of y quantity squared. And then I'm just going to plug this stuff in. So we have the square root of, I'm actually going to put the cosine theta first because I like to have leading terms that are positive. Cosine theta f prime theta quantity squared. Oh, no, sorry. Minus f of theta sine theta. That quantity squared. Uh-oh, here we go. And then plus f of theta cosine theta plus sine theta f prime. And I do apologize if you don't like how I ordered all of these different terms. We need to simplify this. Hopefully, hint, hint, this simplifies greatly. But to convince you that it will before I do it, I mean, when we're simplifying things in math and there are squares and sines and cosines involved, like we know that it's going to simplify at least a little bit because sine squared plus cosine squared is 1. All right, let's go. All right, it's a little bit tedious. You can fast forward if you need to here, but I'm about to expand everything underneath this radical. All right, so we're going to get a cosine squared and then an f prime squared. Cosine squared theta times an f prime theta. I'm going to quantity squared. Minus just expanding a binomial. We're going to get 2ab, so 2. And I'm going to write this strategically. Sine theta cosine theta. F theta, f prime theta. All right, and then we're going to get a plus the second term, b squared, f theta quantity squared, sine squared. Right, that's just the first term. I'm going to go down here for the next one. Plus, and then we have that's another cosine squared. Hint, hint. F theta quantity squared. Plus 2, once again, sine theta cosine theta, f theta, f prime theta, and then plus sine squared theta, f prime squared. Awesome. This is all underneath this radical. Hopefully things are going to simplify. Let's see if they do. All right, and look at that. They immediately do. Right, negative 2 sine cosine f theta f prime theta. That cancels with the positive 2 sine cosine f theta f prime theta. All right, I was strategic. I wrote them exactly the same way, so it might have been a little bit more obvious. Let's go ahead and take everything that's left to the next page just for organization. But I see some cosine squareds. I see some sine squareds. Hopefully some factoring will lead to some ones. Let's see if it works. All right. Just go ahead and grab all of it. Take it to the next page. And there we are. All right, so we are left with, we got a cosine squared. Theta f prime quantity squared. All right, that went away. We have a plus f theta quantity squared sine squared. All right, but we also have a plus cosine squared theta f theta quantity squared, and a plus sine squared theta f prime theta squared. And I believe we are going to start canceling out because I see a common factor between these two, right? We have a sine squared theta cosine squared. Both of these two terms have an f theta quantity squared. So f theta quantity squared, right? That is multiplying the sine squared and the cosine squared. Sweet. There is our first one. And then over here we have a sine squared theta times an f prime theta quantity squared. And you know what? I'm gonna go ahead and write that thing first like I did previously. So we have an f prime quantity squared here. So that's sine squared. And then we have the same thing over here. All right, that's a cosine squared. All right, that is also a 1. We are left with, and here it is. All right. Oh, you know, I've forgotten this entire time. And people might have been screaming at home. There's a delta theta on the outside of every single one of these radicals. All right, so we've the radical. Let me not forget the delta theta right now. All right, we have f of theta squared, which is really just r, and then we have f prime of theta quantity squared, which is r prime, right? Very simple at the end of the day, some nastiness, but this nastiness was necessary because the derivative for polar is a little bit different than the other ones. All right, let's go ahead and get that final answer just to be legit. But so we have a delta L is equal to r squared plus r prime squared, delta theta, and then we are going to look at the length as a limit where delta theta is getting small. All right, this should be a sum. And this becomes, right, theta 1 to theta 2, your bounds, of r squared plus r prime quantity squared, all rooted d theta. There is our polar arc length. Woo! All right, this one ended up being a little bit different, right? The other ones were 1 plus the derivative or derivative plus 1 squared, all that stuff. The parametric one, you took two derivatives. This one, the r, you're not taking a derivative of. Like your actual function is actually, unlike the other ones, your actual function that you're given is appearing in this arc length. All right, and you also have the derivative. So this one's a little bit different. Let's go ahead and get all of the parametric forms down. Sorry, not all the parametric forms. All of the arc length forms down, including parametric. And then we'll do some examples. Just so there's a slide in this video that you can pause off, take a screenshot of, or whatever works for you. Here are the arc length formulas. The arc length formulas. All right, given a function of x, all right, so Cartesian. All right, if you're given a function of x, then your integral would be for arc length, right, from x1 to x2, right, your bounds of, that's the sloppiest radical I've ever drawn, right? So is that now? Oh my gosh, that'll do. 1 plus the derivative of the function quantity squared. Don't forget the squared dx. Right. That's it for if you're given a function of x. If you're given a function of y, very similar. Let me fix that y too. My handwriting isn't the best, but it's getting particularly sloppy here. Your bounds. Right. Once again, 1 plus f, the derivative of the function with respect to y squared dy. Okay. That's for Cartesian. Let's do it over here. For parametric. Right? Given a function x of t, or you know what, let me make it a little more clear. Right? Given a function, given a set of parametric functions, the x function, I'm just going to do this with f and g, right? The x function being f of t, the y function being g of t, the arc length of this set of parametric equations from some value t to some second value t2. We have the derivative of the x function squared plus the derivative of, not the x function again, the y function, right? Quantity squared dt. Can't forget these squares are popping up everywhere. And then the last one, right, polar. Polar is a little bit different in its proof, but given a function r is equal to some function of theta, right? The arc length of that function from some value theta to some second value theta 2. A little bit different. There's no one, there's not all derivatives, but the actual function that you're given, and I can even write it like this: f of theta, the function that you're given, quantity squared, don't forget the square, plus derivative of that function, quantity squared, right, d theta. Right. Here are your arc length formulas. And I could have been a little bit more creative with color, but I did not, and I apologize. There it is. Let's use it a few times because that's a lot of information. Let's actually apply it. All right, let's start by looking at the perimeter of the following polar graph. So you're gonna have to think about which formula from the previous page is relevant. All right, let's look at the perimeter of 1 plus cosine theta. So as Mr. Schwartz said last week, and as I think every single one of your math teachers has always said, drawing a picture is going to give you a tremendous amount of insight. So let's go ahead and draw the curve 1 plus cosine theta. Right? So 1 and 1, this is going to be a cardioid. Since right, this is going to be a cardioid. If I plug in 0, cosine of 0 is 1, so we're going to start at 2. And then it's going to, I'm not too concerned, this is going to like do the little heart thing. Bounce. There we are. Cool. All right, so we want to figure out the perimeter of this cardioid. Before we proceed, stop and think. Do we need to actually find the perimeter of this cardioid? I have some strong opinions about this. Right? Can we not just do what Mr. Schwartz said last week, or last lesson, like 5,000 times? Can we just not use symmetry? Let's look at this graph from 0, theta equals 0, to theta equals pi, and then just double it. So we are going to take the arc length, let's call it L. We want the length from 0 to the theta equals pi, and we want to double it. So we're going to double the length from 0 to pi of, right, this is polar. So polar is going to be the function given squared plus the derivative of the function given squared d theta. All right. Okay, so r here is 1 plus cosine. That's going to be quantity squared. Let's not forget the radical. And then the derivative of this thing is going to be 1 plus, or not 1 plus, 1 goes away, a negative sign. Quantity squared. D theta. All right, simplifying this further, we're going to get, once again, 2, 0 to pi. We're going to get a 1. We're going to get a 2 cosine theta. We're going to get a cosine squared theta. And then we're going to get a positive sine squared theta. D theta. And let's once again not forget the radical. Cool. All right, cosine squared, sine squared. That's just 1. Wonderful. We now have 2. 2 plus 2 cosine theta. D theta. All right, we need to figure out how to evaluate this integral. Take it to the next page. We got 2, integral from 0 to pi, radical, 2 plus 2 cosine theta. And I apologize that my 2's look completely different. And also, this is where I encourage you to pause the video and try to do this integral on your own. Because I know of several ways to do it, and I'm actually kind of curious to how you might intuitively do it. It's not necessarily an easy one. Certainly easier than the ones we're going to do when we start getting to our integrations technique unit. But how would you approach this? So before I do anything, right? I think I'm actually going to do this 2 ways. Before I do anything, I'm going to take out this 2, right? And what does that mean? I'm going to first of all factor out the 2 from those 2 things. And then just take it out of the radical. I'm going to have a 2 root 2, 0 to pi, the square root of 1 plus cosine theta, d theta. All right, so this 2 root 2, just going to sit on the outside. I want to focus with just with 1 plus cosine theta. How can I integrate that? One way to do it would be to try to force some u substitution. Right, because I have a cosine theta here. How can I get myself a sine theta and then do a u sub problem? Right? And the way I see I can add a sine is I'm going to multiply this radical by the square root of 1 minus cosine theta over the square root of 1 minus cosine theta. I'm going to multiply this whole fraction. What that leaves me with is 2 root 2, 0 to pi, and I'm going to have on the top the square root of 1 minus cosine squared theta, and on the bottom I'm going to have the square root of 1 plus cosine squared theta. Cool. Of which, d theta, of which the top is just the absolute value of sine. All right, but what is sine between 0 and pi? Sine between 0 and pi is always positive. So I'm going to go ahead and get rid of that. And what this becomes is 2 root 2 from 0 to pi of sine over 1 minus cosine, or sorry, 1 plus cosine squared theta. And actually, not a square, my bad. This shouldn't even be a minus. It should a plus. It should be a minus cosine theta. Hopefully you guys caught that. Minus. All right, I've set myself up for a u sub here. Sweet, I got a cosine and a sine. All right, that's way number 1. All right, way number 2, let me go ahead and add that d theta there. Way number 2, I think is a little bit more elegant. Let's utilize some trig formulas. Right, I've already taken out this this root 2, but what I'm going to do is I'm going to introduce another 2. Let me go ahead and erase this. Because in my alternative method, I'm going to multiply underneath the radical by 2 over 2. And then what I'm going to get is I'm going to get 1 plus cosine theta over 2 with a 2 in the top, so another root 2, I'm going to get a 4 on the outside. 0 to pi, square root. Boom. All right, that this 2 right here got pulled out, and then this root 2 and this root 2 combined to a 2. Those two became a 4. FYI. Okay, so either of these two integrals I suggest doing. Right. This one over here I think is a little bit easier because 1 plus cosine theta over 2, all square rooted, that's just cosine theta divided by 2. That is an identity. Right? This is way easier to integrate than this problem right here. Right? I am going to finish this problem out so that we can actually get an arc length. I'm going to do it with this second one. I don't feel like doing this u sub. If you're going to do u sub, I would probably call u cosine theta. That way du, or du is negative sine theta d theta. Right? So then that the numerator becomes, what would it be? Just a du. You got a 1 in the numerator. You're going to have 1, I believe, minus u. Yeah, so 1 over 1 minus u. Not too bad. But this one's better. I'm going to take this one to the next page. We got 4, 0 to pi of cosine theta divided by 2 d theta. This is our length. This is, don't forget, the 2 is embedded in here. 0 to pi is half the perimeter, but the 2 is embedded. So we're gonna get that full perimeter. So we need to find the antiderivative of cosine theta over 2. So I'm just gonna I have a feeling sine's involved. Right, theta divided by 2 is going to be involved. What's the derivative of this? That's going to be cosine theta divided by 2 times the derivative of what's inside. Chain rule, so 1/2. Right? That's not what I want. I don't want a 1/2. I want a 1, so I'm just going to put a 2 here. That means there's going to be a 2 here. Those are going to cancel. This is my money. This is what I want. So we got 4, and then times 2 sine theta over 2. Evaluated at pi and 0. Cool. All right, and then let's just do it. So you plug in pi into this thing, you're going to get sine of pi over 2. That's 1. So we're going to get a 2. So we have 4 here. Minus, and then you plug in 0, you're going to get a 0. So minus 0. So look at that. 8 units is the perimeter. That ended up being a real nice, real pretty. That makes me a happy camper, right? It's a camp. And you know what? I'm actually going to stop there. I think one example is enough. I mean, at the end of the day, utilize your graph. Try to make your life easy as you did with area, but also you can do this with arc length. What you need to know are these formulas. And at the end of the day, then it's just an integration techniques problem, which you'll get plenty of practice in class. So we'll stop there. I'm not going to make you watch any more examples. One example I think is enough. We did a polar one. And you just need to know the different forms, right? If you're given a function of x, this is the formula that you use. If you're given a function of y, it's pretty much the same thing. You're just using the function of y. All right. If you're given a parametric, you're going to have 2 derivatives. And when you're given polar, you're actually going to be using the radius and the derivative of the radius. So that is, I think, the most out of touch one. I think it's a little bit different than the other ones. So I'm glad we did that as our example. Right. Going back to the first slide, which is actually way over here, we looked at the mean value theorem. All right, we looked at the mean value theorem. A, to review it, but B, also to use it in our derivations of these formulas. Right? When we derived these formulas, we needed to know that we could take a secant line. In our case, dy over dx, or dx over dy, or dx over dt. We needed to know that we could take a secant line and turn it into a derivative. And we needed to know that within a smooth curve, there exists a point where the derivative is the same as the secant line. Right? So that's why we were able to turn our slopes into derivatives. All right, and so all of these problems require that the curve that you're taking the arc length of to be smooth. And we only did one example. I hope that was enough, but you will be able to work with some people in class and get some more examples under your belt. I think watching me do examples is not as effective as you doing examples yourself. So hopefully you'll find a lot of insight in doing some problems later. And I do recommend, just if you're still here, that means you're studious in the first place. So that's good. I also recommend just skimming through 7.4, 10.3, and 10.5, maybe even reading it in depth before next class so that you have a little bit more preparation. I think that'll help wonders. Right. Once again, the textbook is going to be a really good friend, not only because it's a good friend in general, but because of the online format and the digital format that we currently find ourselves in. So go ahead and read those chapters, and I will see you eventually. Here's some music to help me fade away less awkwardly.